Hello everyone, my name is Alec Edwards and I'm going to be presenting Fossil. Fossil is a software tool for the formal synthesis of Lyapunov functions and barrier certificates using neural networks. So this is some work by myself and my co-authors from the Oxford Control and Verification Group within the Department of Computer Science at the University of Oxford. I'm going to jump straight in with the motivations behind this work. We're interested in the stability and/or safety analysis of nonlinear autonomous systems modeled as differential equations of the form x dot equals f of x. In particular, we want to look at synthesizing Lyapunov functions to certify the stability of a system, or alternatively, barrier functions to certify the safety of a dynamical system. In general, I'll refer to both of these as certificates and denote them as C of x. It's worth noting that there are other alternative approaches already to synthesize these functions, the most notable being sum of squares methods. But in general, these introduce numerical relaxations, which can, of course, create errors. So in this work, we want to focus on sound and preferably automated synthesis approaches. So the first place to begin is with the definition of a Lyapunov function and what we mean by stability. For this, we need to assume we have some equilibrium point for our dynamical system, such that the dynamics of the system at this point are equal to 0. What we want to do is we want to certify the stability of this equilibrium point within some domain as a subset of the entire domain. And here, by stability, we just mean we want to verify that all trajectories starting within this domain D converge towards the equilibrium point. It's worth noting that without loss of generality, we can assume that this equilibrium point is the origin. To certify this stability, we can synthesize a Lyapunov function, which is a function of the state that must satisfy the following three properties. Firstly, it must be lower bounded at the equilibrium point. It needs to be positive everywhere else, i.e. the function has to be positive definite. And finally, we want the function to have a negative time derivative or negative Lie derivative. This derivative is easily calculated using the gradient of the function and the dynamics of the system coupled with the chain rule, and essentially ensures that the trajectories of the system converge towards 0. If you're not familiar with Lyapunov functions, you can just easily interpret them as energy functions where the energy necessarily decreases with time. So now that we've characterized this notion of stability, we can extend it towards safety by now considering two given sets. Firstly, x0, a given initial set, and a given unsafe set xu. And the goal here is to ensure that there is no trajectory starting within this initial set that enters the unsafe set over some domain D. And if we can verify this, then this is our characterization of a safety problem. As you can see in this example here, this is just an example dynamical system with an example initial set in green here and an example unsafe set. And the goal would be just to verify that no trajectory starting in this box here can enter this set over this entire domain. And as before, we can verify this by synthesizing a barrier function or a barrier certificate. As before, this requires three conditions. Firstly, we want the barrier function to be negative in the initial set. We want it to be positive in the unsafe set. And once again, we have this set invariance property on the time derivative or the Lie derivative. Instead here of considering the time derivative of the function everywhere in the state space, we're just interested in where the barrier function is equal to 0, and there we require that the time derivative is strictly negative. So this is equivalent to saying we want the system trajectories to point inwards along the 0 contour of the barrier function. It is worth noting that other characterizations of barrier certificates do exist, but this is what we're sticking with in this work. So now that we've characterized what it is we want to synthesize, what does this leave our overall problem as? Well, we want to find whether there exists some certificate, C of x, such that for all x in our domain, we satisfy either the Lyapunov conditions if we want to verify stability, or the barrier conditions if we want to verify safety. So our approach here to solve this second order formula is to split the existential and the universal quantifiers and decouple the problem of guessing a candidate solution, a candidate certificate, and checking or verifying the certificate And we can do this using an inductive synthesis technique. To do this, we need to sample a finite set as a subset of our entire domain. And using these finite data points, we use an inductive procedure to guess a candidate solution such that this candidate function satisfies the required certificate conditions over all data points in our finite set. Using this candidate solution, we can then check it over not just the finite set, but over the entire domain. And hopefully it's valid over this entire domain. But if it isn't, we want to obtain some place where it isn't, and we label this as a counterexample. We can then augment our original data set with this counterexample and re-perform our inductive procedure with this new knowledge of where we were originally wrong. And this procedure should continue until we synthesize a valid solution. So the most common approach to this is known as counterexample guided inductive synthesis, or CGIS. This generally consists of two opposing components. The first is a learner, which uses inductive methods and numerical computations to generate these candidate solutions to our problem. These candidates are then passed to its opponent, the verifier, which seeks to certify the validity of these solutions over some domain using some formulae. And if it can't certify the validity, it provides this counterexample where the candidate solution is not correct. This opposing game between the learner and the verifier continues indefinitely until the verifier determines that the solution is valid, hopefully, or until you just break the loop. The task here is to identify what our learner should be and what our verifier should be. And to begin with, we're going to consider the learner. We want the learner to be a neural network, ideally. They're an attractive choice because they're very easy to train for a wide variety of very flexible structures. And this flexibility allows them to approximate any number of different functions. Firstly, this flexible structure comes from their neural structure, in particular the number of hidden layers and the number of neurons within these layers. And as you're aware, if you know the weights and the biases for these corresponding layers, you can write down a closed form expression for the neural network, as long as you also know the all-important activation function. And this is perhaps where even more of our flexibility comes from. So we can choose to use, say, polynomial activation functions and obtain candidate Lyapunov and barrier functions that represent what we might normally expect these functions to look like, such as if we took a sum of squares approach, they might look more like typical energy functions that we would expect. But alternatively, in the same procedure, we can choose to use more neurotypical activation functions, such as hyperbolic tan or soft plus, which is a smooth ReLU function, which are known to be highly expressive when used within neural networks. The second task is to identify the verifier, the common choice for which is an SMT solver. If you're not familiar with SMT solvers, they generalize the Boolean SAT problem from solving the satisfiability of Boolean formulae to formulae over the real numbers. For instance, with this formula here, if you provided it to an SMT solver, the SMT solver would try to find a value for x and a value for y such that the formula is satisfiable. And if it can't do so, it will determine that the formula is unsatisfiable. Common examples of these SMT solvers include Z3, which is made by Microsoft and provides a decision procedure over polynomial formulae, or as an alternative, there's DeReal, which allows reasoning over both polynomial and non-polynomial formulae. By non-polynomial here, I mean, for example, trigonometric or hyperbolic formulae, which of course is essential to us if we want to use these neurotypical activation functions, such as hyperbolic tan. It's worth emphasizing that a key property of these SMT solvers is that they are sound. For our purposes, this means that if a given formula is satisfiable, they will provably determine that it is satisfiable, which is essential to the formality of our verification procedure. Now that we've covered the relevant background material, I'd like to move on and start discussing our solution to this problem, which, as I mentioned before, is called Fossil and is a software tool for the formal synthesis of these Lyapunov functions and barrier certificates. The key part of Fossil really is that it combines expressive neural network templates with an enhanced CGIS loop that I'm going to detail in a moment. Fossil also leverages multiple SMT solvers, namely Z3 and Dureal, as I've just mentioned. And I'm also going to demonstrate that the tool is both scalable and robust. I think the best way to describe how Fossil works and the research ideas behind it is to describe to you what we call the component structure. So this diagram here represents the component structure within Fossil. And it might look familiar because, of course, it's a CGIS loop. We have a learner component and a verifier component. But we also have these two intermediate components that I'm going to describe in detail shortly. What I'd like to do is essentially take you through each component in turn, how it works and how it works with all the other components to synthesize these certificates. So to begin, let's discuss what it takes as inputs. So of course, the first input is the dynamical system in question that you're seeking to verify either the stability or the safety of. Then is the domain of verification. And for the barrier certificate case, this will include the corresponding initial set and unsafe set as well. This term theta characterizes the template of the neural network we want to use, so the activation functions, the neural structure, things like that. And S is our finite set of data points S. And these four are passed to our first component, the learner, which, as I've mentioned, is a neural network. And the key part really of any neural network is its loss function. So as stated, for this, we assume we have some sampled set of data points S, or for the barrier certificate case, we have three sets, one for the initial set, one for the unsafe set, and one for the entire domain. So we want our loss function to help guide the neural network to satisfy the certificate conditions. And we can do this by penalizing where it unsatisfies the conditions. We can do this using the max or the ReLU function. So for instance, if you consider this first term here, this will penalize all points within our finite set where our Lyapunov function is negative, when of course it should be positive. Similarly, this term here will penalize anywhere where its time derivative is positive. Also similarly for the barrier function case, this will penalize positivity in the initial set, negativity in the unsafe set. And this third term is slightly more complicated because rather than just consider all the data points where the barrier certificate is equal to 0, which of course over a finite set could be very small or even empty, we consider some small belt around 0 and use these points for learning instead. It is worth noting here that perhaps only penalizing where our functions unsatisfy the conditions is a bit naive, when in addition we could also reward where they do satisfy the conditions. And yes, we can enhance this loss function to do this. So the motivation behind this would be to help improve the robustness of the procedure. For instance, we might have data points within our finite set that are close to the boundary of the conditions, by which I mean, say we want the Lyapunov function to be positive, and we are positive, but we're still very close to 0. There could be further data points near that are not in our finite set that are negative when they should be positive. So because these won't affect the loss function, we want to help drive the function to be more positive here. So we can do this using a leaky ReLU function. But the problem is we don't want to overdo this because regions that are significantly satisfying the relevant conditions are useless to us if we still have regions where the conditions are unsatisfied. So we can kind of bound this reward using instead of saturated leaky ReLU. So the learner provides to us this numerical neural network that we need to convert into a proper candidate solution to our problem that can be passed to our SNT solver. For this, we have our first intermediary component, which we call the translator. So as in the name, the goal of this is to translate the neural network to a symbolic formula. From a programmatic point of view, this is quite easy to do by simply noting that as long as we have the weights and the biases of our neural networks, we can find some closed form expression for it. And similarly, if we use the chain rule, as before, we can find the time derivative of it. All we need to know as well are the dynamics of the system, the activation functions and its derivative. And these are all things we know, so we can find these expressions, which are what we need to perform for verification. The issue here, though, is that we're converting an object from essentially a floating point domain to a symbolic domain. And these floating point coefficients are likely to be ill-conditioned. They might be very small, or they might have lots of trailing decimals. And providing these to our verifier could essentially give the verifier a hard job. It can make the verification very difficult or even intractable. So our solution to tackle this is essentially just to simplify the expressions for the candidate solution. We truncate long coefficients and we ignore ones that are too small, with the hope that the function will still behave similarly to the old one, but that we will aid the verifier significantly such that this is now a worthwhile thing to do. So with this candidate solution, we can pass it to the verifier, which, as I mentioned, is going to be an SNT solver. So how do we actually perform this verification step? Well, the SNT solver accepts the negation of the certificate conditions and tries to find a witness to them. So, for instance, what we mean by this, for the Lyapunov case, we ask the SNT solver to find if there exists such an X such that in our domain, either the Lyapunov function is negative or its time derivative is positive. The SNT solver will, if it finds such an X, then that means we found a place where the Lyapunov conditions are invalidated. So our Lyapunov function is not a valid Lyapunov function. Similarly, for the barrier case, we ask it to find an X such that we are positive in the initial set, negative in the unsafe set, or where the time derivative is not negative in where the barrier function is equal to 0. And of course, there are two key outcomes here. The first is that the SNT solver determines that the formula it's provided is unsatisfiable. This would mean that there's no point in our domain where our certificate conditions are invalidated, or in other words, our certificate is valid, we've completed synthesis, and we've certified the stability or the safety, depending on what we were looking at. The more interesting outcome is that the SNT solver determines the formula is satisfiable. As I said, this would be a counterexample to our problem. It's where our candidate solution is currently incorrect, and we need to work to improve that. So as with our inductive synthesis procedure, we can augment our original dataset S with this point and continue further learning. The issue here is that we're dealing with machine learning and neural networks, which generally rely on quite large data sets. So this single data point probably won't have much of an impact. So to address this issue, we have our second intermediary component, which we call the consolidator, which takes as input this single counterexample. And the goal of the consolidator is to augment this counterexample to enhance the learning that the learner can achieve from just this one counterexample. So really the idea of this is to maximize this communication between the verifier and the learner. And there are two main approaches that we take to do this. The first is by noting that there are likely further invalid points near our original counterexample. So we can just generate random samples near this counterexample, check if they also invalidate the conditions, and if they do, add them to our counterexample set. Secondly, if we notice that the functions we're dealing with are almost everywhere differentiable, we can perform either gradient ascent or gradient descent to find, firstly, points of greater violation to the certificate conditions, but also ideally points of max violation. If we do this, we have potentially found even better counterexamples than the SNT solvers found, which arguably provide even better information to the learner on what it's doing wrong so far and why it's not valid. So we can take these sample trajectories and our sample counterexamples and augment the original dataset S with this new big counterexample set and pass them back to our learner. This loop then continues until we either run out of some arbitrary number of loops that we've predetermined, or until the verifier determines that we found a valid solution. So the real key part of Fossil is this enhanced communication between the learner and the verifier, provided by these two intermediate components, that we call the translator and the consolidator. In our experience, this enhanced communication not only improves the robustness of the CGIS procedure for synthesis of these certificates, but also improves the speed at which it's able to do so. Because of this, I'd like to take some time now to demonstrate the efficacy of the tool using some experimental results. So to begin with, let's consider some results for Lyapunov functions. This table involves 4 different dynamical systems, each of which admit a non-polynomial global Lyapunov function. Of course, we're considering verification over some bounded domain, so instead we try and synthesize a Lyapunov function over some bounded domain defined by a hypersphere of radius rho, and consider that the larger the domain is, the better we're doing. We present here in the table the maximum rho, the maximum radius that we could achieve for the tools we were comparing against. For instance, we compare against 2 other counterexample-based tools, one of which uses a linearization procedure that is invalid for radiuses greater than 1. So compared to these 2 tools, we find that we are able to synthesize Lyapunov functions using Fossil for domains that are up to 1,000 times larger. And we're able to do this up to 100 times faster as well. We also compare against the canonical sum of squares method. And from a synthesis perspective, our synthesis times are very comparable. But it's worth noting that sum of squares doesn't produce sound or verified candidate solutions. So to compare like for like, we pass these solutions to a verifier, but of course, they're not necessarily well-conditioned polynomials. So this procedure can occasionally time out and is not successful. So now moving on towards some barrier certificate examples. In this table here, we have quite a wide range of example systems for which we want to synthesize barrier certificates for. For instance, we have some higher order dimensional systems, including up to an 8th order system. We are able to synthesize a barrier certificate for a hybrid system, a semi-applied obstacle avoidance problem, and also a dynamical system using sine and exponential terms, of course, leveraging the real SMT solver I mentioned before. As before, we compare against another counterexample-based method and find that Fossil is up to 100 times faster than this procedure, but interestingly, it also uses up to 1,000 times fewer samples. This can be attributed firstly to our enhanced CGIS loop, which improves the robustness of the procedure, but also the power of our loss function training the network, which enables it to generalize well and learn quickly. Once again, we compare to sum of squares methods, and from a synthesis approach again, we are comparable, but as before, the verification procedure for sum of squares can time out. I wanted to take this opportunity to illustrate some of the barrier functions that Fossil is able to synthesize. So these left-hand plots are the surface plots of the barrier functions, and the right-hand ones show the dynamical system involved. So this top system here is the dynamical system containing sine and exponential terms, as I mentioned before. This black line here is the zero contour of the barrier function. So as you can see, this black line serves as a separator or a barrier between this green initial set and this red unsafe set, with the system trajectories pointing inwards along the zero contour. In contrast, this system here has polynomial dynamics, but the relative closeness of the unsafe sets and the initial sets makes the zero contour of the barrier function quite a specific shape. So this is a comparatively more difficult problem as well, and is achieved using a neural network with 2 hidden layers of sigmoid activations. I think there's around 20 neurons in each layer there. If you're interested, this top system here, this barrier function is a neural network with a single hidden layer of soft plus activation functions. I think around 20 neurons again. We've established that the tool is scalable and can perform for a wide variety of benchmarks. So now I want to address the robustness of the tool. So generally, due to the verification step, we're relying on fairly small neural networks. In general, we find success with neural networks with around 2 hidden layers with up to 20 neurons in these. So these shallower neural networks are less robust than their deeper counterparts, with the random initialization of their weights and biases having more impact on their results. And of course, we're also relying on the randomness of the original sampling of our finite data sets. So we wanted to establish whether or not the tool is robust to these random initializations. To do this, we considered a basic Lyapunov synthesis problem, where we choose to vary the width of the neural network, a single layer neural network with varying numbers of neurons. We consider a different domain size, so a different hypersphere of different radii for a given dynamical system. And what we want to do is we want to repeat the number of times we run the tool for each of these and record the average time and the number of failures. So the results of these experiments are illustrated in this figure here, where along the horizontal axis, we have the varying domain radius of verification. Along the left vertical axis, the lines represent the average computational time of the procedure over 100 runs. The right-hand axis is the stars, and this represents the number of failures of the procedure over these 100 runs. And by a failure, we mean either the verifier has timed out through some predetermined timeout, or the procedure has gone through a set number of CGIS loops and we've terminated. So we consider both of these over a varying number of network widths for a single hidden layer. So H here denotes the number of hidden neurons within this layer. So we go from 2 hidden neurons, 10, 50, and 100. The first thing to note is that for just 2 hidden neurons, it's clear that the procedure doesn't perform very well. This is expected because essentially the neural network is not very robust for such a small number of hidden neurons, and it's not able to be as expressive. So it's not able to learn a suitable Lyapunov function for these larger size domains. As we increase the number of hidden neurons to 10, we get a better performance. But again, it's not able to be as expressive as we might like it to be. Perhaps most interestingly is that 50 hidden neurons performs much better than 100 hidden neurons, even though you might expect otherwise. The reason for this is because although 100 hidden neurons can be more expressive, essentially the expression for the neural network becomes much more complicated, and it's then harder for the verifier to perform the verification procedure. So it's clear that there's some sort of middle ground here, where if we choose the right number of hidden neurons, we get sort of a Goldilocks ground between both the verifier and the learner, where you both have a neural network that is both expressive enough to solve the problem that you're trying to solve, but is not too complicated for the verifier to perform verification on. So in conclusion, we've demonstrated an easy-to-use tool Fossil, which is available at GitHub. This tool is useful for the automated and sound synthesis of Lyapunov and barrier functions, and provides a flexible architecture for a breadth of use cases. We've also validated the tool for both robustness and scalability, and we also have ongoing work looking at synthesis of these functions for stochastic models and controlled models, and also inclusion of further SMT solvers, such as using a wrapper like PySMT. Thank you for your attention.